This is the most failed question in physics paper 2, and I'm going to teach you how to answer it in less than 5 minutes. So let's start with question 1, then we walk all the way up to the same question, which is question 11. So pay particular attention how I answer the questions and how I explain the questions. If you haven't subscribed, please do so. If you haven't liked, please do so.
Into it. Question 1. Measurement and micrometer screw gauge. Question 1 tells us that in scientific measurements, the accuracy and precision of an instrument is key to obtaining the right measurement. Figure 1.1 shows the reading on a measuring instrument. Looking at the diagram, we can see a thimble scale with a main scale in millimeters and a circular thimble scale. This is clearly a micrometer screw gauge. Part A asks us to name the measuring instrument. The instrument is a micrometer screw gauge, one of the most precise measuring instruments in the physics laboratory, capable of measuring to the nearest 0.01 millimeters. Part B asks for the accuracy of this instrument. The accuracy of a micrometer screw gauge is 0.01 millimeters. This means it can measure lengths to within 1/100th of a millimeter, far more precise than a standard ruler or even a vernier caliper. Part B2 tells us the instrument has an error of negative 0.06 millimeters and asks us to calculate the correct measurement. Looking at figure 1.1, the main scale reads 3.5 millimeters, the sleeve shows 3.5 on the main scale. The thimble scale reads 20, which adds 0.20 millimeters. So the raw reading is 3.5 plus 0.20, which equals 3.70 millimeters. Now, the error is negative 0.06 millimeters. This is a negative zero error, meaning the instrument reads 0.06 millimeters less than the true value. To correct for a negative zero error, we add the magnitude of the error to the reading. Correct measurement equals 3.70 plus 0.06, which equals 3.76 millimeters. The correct measurement is 3.76 millimeters. Excellent start. Now let's move into energy and motion with a very visual and satisfying scenario. Question 2 shows a block of mass 200 grams sliding from rest at point A on a curved frictionless path to reach point C. Point A is 25 centimeters high and point C is 12 centimeters high. Point B is at the bottom. Take G as 10 meters per second squared. Part A asks us to define friction. Friction is a force that opposes the relative motion between two surfaces in contact. It acts in the direction opposite to the motion of an object and is caused by the roughness or irregularities between the surfaces that are touching each other. Part B asks for one other effect of friction, apart from opposing motion. Friction produces heat. When two surfaces rub against each other, kinetic energy is converted into thermal energy. Heat is generated at the contact surface. This is why your hands warm up when you rub them together, and why brakes heat up when applied. Another valid answer is that friction causes wear and tear on surfaces over time. Part C asks for the velocity of the block as it passes point B. Since the path is smooth and frictionless, all the gravitational potential energy at A converts fully into kinetic energy at B. A height at A is 25 centimeters, which is 0.25 meters. Mass is 200 grams, which is 0.2 kilograms. GPE at A equals mass times G times height equals 0.2 times 10 times 0.25, which equals 0.5 joules. This equals the KE at B. So half times mass times velocity squared equals 0.5. Rearranging, velocity squared equals 2 times 0.5 divided by 0.2, which equals 5. Taking the square root of 5 gives velocity equals approximately 2.2 meters per second. Part C2 asks for the kinetic energy of the block at point B. We already found this, Ke at B equals 0.5 joules. That is the complete conversion of the gravitational potential energy from point A, since there is no friction. Part D asks us to explain why the velocity of the block reduces when it reaches point C. At point C, the block has risen to a height of 12 centimeters. As it rises, some of its kinetic energy is converted back into gravitational potential energy. The higher the block goes, the more kinetic energy is converted, so the velocity decreases. At point C, the block still has some kinetic energy left, but less than it had at B, because some energy has gone back into GPE. That is why velocity reduces at C compared to B. Now let's move into pressure, both in water and in the atmosphere. Question 3. Pressure, dams and barometers. Question 3, Part A, tells us that an engineer has designed 2 dams to hold water up to a height of 80 meters. Figure 3.1 shows a narrow dam and Figure 3.2 shows a wider, broader dam with a larger base. Part A asks which design we would recommend and why. We would recommend Figure 3.2, the wider dam with the broader base. The reason is that water pressure increases with depth. The pressure at the bottom of the dam is much greater than at the top. A broader base provides a larger area over which this high pressure is distributed, which means the force on the base is spread out and the dam is stronger and more stable. The narrow dam in Figure 3.1 would be at greater risk of collapsing under the large pressure at its base because it has a smaller area to withstand the force. Part A2 asks us to calculate the pressure at the bottom of the dam. The density of water is 1,000 kilograms per cubic meter and G is 10 newtons per kilogram. Pressure equals density times G times height. So pressure equals 1,000 times 10 times 80, which equals 800,000 pascals, or 800 kilopascals. That is an enormous pressure, which is exactly why dam design must be very carefully engineered. Part B asks us to explain briefly how the mercury barometer is used to determine pressure changes in the atmosphere. The mercury barometer works by balancing a column of mercury against the atmospheric pressure. The atmospheric pressure pushes down on the mercury in the trough, which forces mercury up into the sealed glass tube. The height h of the mercury column in the tube is a direct measure of the atmospheric pressure. The higher the mercury column, the greater the atmospheric pressure. If the atmospheric pressure increases, it pushes more mercury up into the tube and the reading increases. If the pressure falls, for example, when a storm is approaching, the mercury level drops. So by reading the height of the mercury column, we can determine and track changes in atmospheric pressure. Part B2 tells us the barometer reads 76 centimeters at sea level, but reads 82 centimeters at the top of a mountain. It asks us to suggest why the barometer might be defective. This reading is physically wrong. At high altitude, such as on top of a mountain, the atmospheric pressure is lower, not higher, because there is less air above. So the mercury column should be shorter at the top of a mountain, giving a reading less than 76 centimeters. A reading of 82 centimeters at altitude is higher than sea level, which is impossible under normal conditions. This suggests the barometer is defective. Possibly some air has leaked into the sealed space above the mercury in the tube. Any air in the sealed space would push down on the mercury and give incorrect readings. The barometer is therefore unreliable and should not be trusted. Question 4. Simple machines, pulley systems. Question 4 tells us that Figure 4.1 shows a block and tackle pulley system with a velocity ratio of 5. And Figure 4.2 shows a differential pulley with 2 pulleys of radii 28 cm and 14 cm. Both systems raise a 60 kg mass. Part A asks for the number of pulleys in the movable block of the block and tackle system. In a block and tackle, the velocity ratio equals the total number of pulleys in both blocks. However, the velocity ratio also equals the number of sections of rope supporting the movable block. With a velocity ratio of 5, there are 5 sections of rope supporting the load. In a typical block and tackle with VR of 5, the movable block contains 2 pulleys and the fixed block contains 3, or some other combination. The number of pulleys in the movable block is 2. This is because each pulley in the movable block contributes 2 rope sections, and with 5 sections total, we need 2 pulleys below and the effort rope accounts for the odd section. Part B, the system has 80% efficiency. Calculate the effort required to move 60 kilograms. The load equals mass times G equals 60 times 10 equals 600 newtons. Efficiency equals mechanical advantage divided by velocity ratio times 100. Rearranging for mechanical advantage, MA equals efficiency times VR divided by 100 equals 80 times 5 divided by 100, which equals 4. Mechanical advantage equals load divided by effort. So effort equals load divided by MA equals 600 divided by 4, which equals 150 newtons. The effort required is 150 newtons. Part B2 asks for the power developed if the machine raises 60 kilograms through 40 meters in 20 seconds. Work done on the load equals force times distance equals 600 times 40, which equals 24,000 joules. Power equals work divided by time equals 24,000 divided by 20, which equals 1,200 watts. However, since the machine is only 80% efficient, the actual power input equals output power divided by efficiency equals 1,200 divided by 0.8, which equals 1,500 watts. The power developed by the machine is 1,500 watts. Part C asks for the distance moved by the effort in the differential pulley when the load is raised 2 meters. For a differential pulley, the velocity ratio is calculated as VR equals 2 times A divided by R minus R, where R is the larger radius and R is the smaller radius. Here R equals 28 centimeters and R equals 14 centimeters. VR equals 2 times 28 divided by 28 minus 14 equals 56 divided by 14, which equals 4. So the velocity ratio is 4. The distance moved by the effort equals VR times distance moved by the load. So effort distance equals 4 times 2, which equals 8 meters. The effort moves 8 meters when the load rises 2 meters. Part D asks for the advantage of a differential pulley over a block and tackle. The differential pulley does not require a ratchet or locking mechanism to hold the load in place when the effort is released. The load stays in position due to the friction in the chain and pulleys. This makes it safer and more practical for sustained lifting, such as in workshops and garages. The block and tackle may slip back if the effort is released without a locking device. Now we move into thermal physics with latent heat. Question 5 is about an immersion heater boiling water, and it asks some really deep questions about why water needs energy to boil and what happens during that process. Question 5. Latent heat of vaporization. Question 5 tells us that a 200-watt immersion heater is lowered into a jar of water and switched on. 0.1 kilograms of water boils away. The specific latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. Part A asks us to explain why heat is needed to boil water away. When water is at its boiling point, the molecules at the surface have enough kinetic energy to partially overcome the attractive forces holding them together. But to completely break free from the liquid and become gas, water vapor, the molecules need additional energy to fully overcome these intermolecular attractive forces. This extra energy is called the latent heat of vaporization. It does not raise the temperature, it goes entirely into breaking the bonds between water molecules so they can escape into the gas phase. Without this energy input, the molecules cannot escape the liquid, no matter how long you wait. Part A2 asks why the temperature of the water remains constant during boiling. This is a beautifully important concept. During boiling, all the energy supplied by the heater goes into breaking the intermolecular bonds between water molecules, converting liquid water into water vapor. None of the energy goes into increasing the kinetic energy of the molecules. Since temperature is a measure of the average kinetic energy of the molecules, and the kinetic energy is not increasing during boiling, the temperature stays constant at 100 degrees Celsius throughout the boiling process. Only when all the water has vaporized would additional energy start raising the temperature again. Part B asks how long it takes for the 200-watt heater to boil away 0.1 kilograms of water. Energy needed equals mass times specific latent heat of vaporization. So energy equals 0.1 times 2.26 times 10 to the 6, which equals 226,000 joules. Power equals energy divided by time. Rearranging, time equals energy divided by power. Time equals 226,000 divided by 200, which equals 1,130 seconds, that is about 18.8 minutes. Part C asks us to suggest what would happen to the water molecules that boiled away into the atmosphere. When the water molecules enter the atmosphere as water vapor, several things can happen. The hot vapor molecules rise into the cooler upper atmosphere. As they rise and encounter cooler temperatures, they lose kinetic energy and slow down. The intermolecular attractive forces begin to pull them back together. This is the process of condensation. The water vapor condenses into tiny liquid water droplets, which may form clouds. Eventually, when enough droplets combine, they become heavy enough to fall back down as rain or precipitation. So the water molecules undergo a complete water cycle: evaporation, condensation, and precipitation. Question 6 takes us into the physics of sound, specifically how sound travels as a longitudinal wave through air molecules. Let's visualize what is actually happening at the molecular level. Question 6. Sound waves. Question 6 tells us that sound is a longitudinal wave in which oscillations take place in the direction of the wave. Part A asks us to draw the arrangement of air molecules as a sound wave passes, labeling the wavelength with the symbol lambda. When a sound wave passes through a column of air molecules, it creates alternating regions of compression and rarefaction. In a compression, the air molecules are pushed closely together, draw the molecules crowded close together in that region. In a rarefaction, the molecules are spread further apart than normal, draw them spaced out widely in that region. The pattern repeats: compression, rarefaction, compression, rarefaction. The wavelength, labeled as lambda, is the distance from one compression to the next compression, or equivalently from one rarefaction to the next rarefaction. Draw your arrow spanning this distance and label it lambda. Part B asks us to explain why the speed of sound does not depend on the pressure of a gas. This is a fascinating physics concept. When the pressure of a gas increases, at constant temperature, two things happen simultaneously. The density of the gas increases because the molecules are more tightly packed together. But the elastic restoring force also increases by the same proportion, meaning the molecules push back harder when compressed. These two effects, increased density tending to slow the wave, and increased elasticity tending to speed it up, exactly cancel each other out. The ratio of elasticity to density remains constant regardless of pressure. Since the speed of sound depends on this ratio, the speed remains unchanged when pressure changes. Part C asks us to explain why the speed of sound decreases at high altitude. At high altitude, the atmosphere is much less dense, the air molecules are further apart. You might think this would increase the speed since there is less resistance. But actually, the lower density at altitude is accompanied by a much lower temperature. Lower temperature means the air molecules have less kinetic energy and vibrate more slowly. It is primarily the lower temperature that causes the speed of sound to decrease at altitude, and since speed of sound is proportional to the square root of the absolute temperature, the colder the air, the slower the sound. Part D asks for the effect produced when sound waves are reflected such that the echoes overlap with the original sound. The effect produced is reverberation. When reflected sound echoes reach the listener so quickly that they overlap with the original sound that is still being heard, the sounds blend together. This creates a prolonged, sustained sound that seems to linger and fill the space. Reverberation is common in large halls, caves, and cathedrals. A small amount of reverberation can make music sound richer, but too much makes speech difficult to understand. Now let's explore light and total internal reflection more deeply. Question 7 uses a semicircular glass block, a classic experiment for studying how light behaves at boundaries. Let's trace what happens as the angle increases. Question 7, light and total internal reflection. Question 7 shows a ray of light I entering a semicircular glass block and striking the flat surface at center C at angle theta. There is a transmitted ray T going into the air, a reflected ray R staying in the glass, and an emergent ray E coming from the curved surface. Part A I asks us to describe the variation of the intensity of the transmitted ray T as angle theta gradually increases. As angle theta increases from 0, the transmitted ray T gradually becomes less intense. This happens because as the angle of incidence increases, more and more of the light is reflected back into the glass rather than being transmitted through into the air. At small angles, most of the light passes through, T is bright. As theta approaches the critical angle, T becomes dimmer and dimmer. At exactly the critical angle, T travels along the boundary and has nearly zero intensity. Beyond the critical angle, T disappears completely, total internal reflection occurs and no light is transmitted at all. Part A2 asks how the intensity of the reflected ray R changes as theta increases. As theta increases, the intensity of the reflected ray R gradually increases. At small angles, only a little light is reflected and most is transmitted. As the angle increases toward the critical angle, more light is reflected back into the glass and R gets brighter. At the critical angle and beyond, all the light is reflected, total internal reflection, and R reaches its maximum intensity. There is no more transmission, so all the energy goes into the reflected ray. Part B I asks which color of light would disappear first from the transmitted ray T as theta increases. The critical angle depends on the refractive index of the glass, which depends on the wavelength, or color, of light. Violet light has the highest refractive index in glass, it bends the most. A higher refractive index means a smaller critical angle. So violet light reaches its critical angle at a smaller theta than other colors. Therefore, violet light would disappear first from the transmitted ray as theta increases. Part B2 asks whether there is any dispersion of colors for the emergent ray E, and to explain the answer. Ray E exits through the curved surface of the semicircular block. Because the curved surface is centered on point C, all rays emerging through the curved surface hit it perpendicularly, at 90 degrees to the surface. When a ray hits a surface at 90 degrees, that is, perpendicular to the surface, there is no bending. No refraction means no separation of colors. Therefore, there is no dispersion for ray E. All colors exit at the same angle and the emergent ray E remains white. Now let's tackle some circuit calculations. Question 8 is about resistors in series, and it tests your ability to read a circuit, complete it, and calculate key electrical quantities. Question 8. Series circuits. Question 8 shows an incomplete circuit with two resistors in series, a 6 ohm and a 12 ohm resistor. The ammeter reading is 0.55 amperes. Part A asks us to complete figure 8.1 by drawing the ammeter, battery, and voltmeter. In a series circuit, the ammeter must be connected in series, in line with the resistors, so all the current flows through it. The battery symbol, two parallel lines, one longer for positive and one shorter for negative, is placed in the main circuit loop. The voltmeter must be connected in parallel across the 12 ohm resistor, one terminal to each end of the 12 ohm resistor, because voltmeters measure the potential difference across a component and must be connected in parallel to do so. Part B asks for the combined resistance of the two resistors. In a series circuit, the total resistance equals the sum of individual resistances. Total resistance equals 6 plus 12, which equals 18 ohms. Part B2 asks for the EMF of the battery. Using Ohm's law, EMF equals current times total resistance. EMF equals 0.55 times 18, which equals 9.9 volts, approximately 10 volts. Part C asks how the combined resistance would change if the two resistors were connected in parallel. When resistors are connected in parallel, the combined resistance is always less than the smallest individual resistance. Using the parallel resistance formula, 1 over total resistance equals 1 over R1 plus 1 over R2. So 1 over total equals 1 over 6 plus 1 over 12, which equals 2 over 12 plus 1 over 12, which equals 3 over 12. Therefore total resistance equals 12 divided by 3, which equals 4 ohms. So the combined resistance decreases from 18 ohms in series to just 4 ohms in parallel. This is because in parallel, the current has multiple pathways, so the overall opposition to current flow is reduced. Now we enter section B. Question 9 is a comprehensive question about electromagnetic waves and their many uses in communication. This is a very important topic with real-world applications that affect your daily life. Question 9, electromagnetic waves and communication. Question 9 tells us that electromagnetic waves transfer energy and information without transferring matter, and that they are transverse in nature. Part A asks which bands of electromagnetic waves have wavelengths ranging from 10 to the negative 5 meters to 10 to the 4 meters. Looking at the electromagnetic spectrum in the correct order from shortest to longest wavelength, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves. Wavelengths from 10 to the negative 5 meters to 10 to the 4 meters span from infrared through microwaves all the way to radio waves. So the bands in this range are infrared, microwaves, and radio waves. Part A2 asks us to explain why visible light can be split into different colors. Visible light is made up of different colors, from violet to red, each with a different wavelength and frequency. When white light passes through a prism or another dispersive medium, different wavelengths travel at slightly different speeds and therefore refract by different amounts. Violet light has the shortest wavelength and refracts the most, while red light has the longest wavelength and refracts the least. This difference in refraction separates the colors, splitting white light into its spectrum. This process is called dispersion. Part B asks us to explain why long wavelength radio signals B can be transmitted over long distances. Long wavelength radio waves, AM radio, can travel over very long distances because they diffract effectively around the curved surface of the Earth and around large obstacles like hills and mountains. Diffraction is the bending of waves around obstacles, and longer wavelengths diffract more effectively than shorter ones. Additionally, long wavelength radio waves are reflected by the ionosphere, a layer of charged particles high in the atmosphere. They bounce back and forth between the Earth's surface and the ionosphere, allowing them to travel thousands of kilometers around the globe. Part B2 asks how the reception of radio wave C, used for television, is achieved, given that they do not bend around hills. TV and short wavelength radio waves have much shorter wavelengths and do not diffract significantly around hills or the curvature of the Earth. To achieve reception in areas blocked by hills and buildings, relay transmitters and satellite systems are used. Signals are sent up to satellites orbiting the Earth, which then retransmit the signals back down to receivers across wide areas. Alternatively, relay stations are placed on hilltops to receive the signal from the main transmitter and rebroadcast it to surrounding areas that would otherwise be in a signal shadow. Part C asks why excessive mobile phone use could be harmful. Mobile phones transmit and receive signals using microwaves. Microwave radiation is absorbed by body tissue, particularly water in the body, and can cause slight heating of tissue. Excessive exposure to microwaves over long periods may potentially cause damage to biological cells, including DNA damage, and has been associated with possible health risks including headaches and, in extreme cases, has been studied in relation to brain tumors. Although the evidence is still being researched, precaution is advisable. Part C2 asks why it would be dangerous to use infrared radiation instead of microwaves for mobile phone signals. Infrared radiation is absorbed very strongly by water molecules in body tissue, far more than microwaves. Significant absorption of infrared would cause much greater heating of body tissue, potentially causing burns, damage to skin, eyes, and internal organs. It would be far too dangerous to use for a device held close to the body like a mobile phone. Part C3 asks for one use of infrared radiation. Infrared radiation is used in remote controls for televisions and other electronic devices. It is also used in thermal imaging cameras, heat lamps for medical therapy, and in fiber optic communications for data transmission. Part D asks for two differences between sound waves and electromagnetic waves. First, sound waves are longitudinal waves, where the vibrations are parallel to the direction of wave travel. Electromagnetic waves are transverse waves, where the vibrations are perpendicular to the direction of travel. Second, sound waves require a material medium to travel and cannot travel through a vacuum. Electromagnetic waves can travel through a vacuum. In fact, they travel fastest in a vacuum at 3 × 10⁸ meters per second. Sound cannot travel in space, but light and radio waves can. Question 10 is a rich question combining magnetism, electromagnetic induction, and transformers. These are 3 deeply connected topics, and understanding them together gives you a complete picture of how electricity is generated and distributed. Question 10. Magnetism, electromagnetic induction, and transformers. Question 10, Part A, shows an iron bar that can be magnetized or drawn into conducting wires. Part A asks us to use domain theory to explain how the iron bar gets magnetized. Inside any magnetic material, there are tiny regions called magnetic domains. Each domain is like a tiny magnet with its own north and south pole. In an unmagnetized iron bar, the domains are randomly oriented, pointing in all different directions, so their magnetic effects cancel out and the overall bar shows no magnetism. When the iron bar is placed in a magnetic field, for example, inside a solenoid carrying current, the magnetic field exerts a force on each domain, causing them to rotate and align with the external field. When most or all of the domains are aligned in the same direction, the entire bar becomes a magnet with a clear north and south pole. This is how the iron bar gets magnetized. Part A2 asks us to explain how wires drawn from the iron bar conduct electricity. Iron is a metal. Metals have a crystal structure in which the outer electrons of each atom are loosely held and can move freely throughout the entire metal. They are called free electrons or delocalized electrons. When a potential difference, voltage, is applied across the iron wire, these free electrons experience an electric force and drift in one direction along the wire. This movement of free electrons constitutes an electric current. The more freely the electrons can move, the better the conductor. Iron has a large number of free electrons per unit volume, which is why metallic wires drawn from iron can conduct electricity. Part B asks us to copy and complete Figure 10.2 to show the secondary circuit connected to the primary circuit for electromagnetic induction investigation. The secondary circuit should show a coil of 5 turns placed near the primary coil, connected to a galvanometer. The galvanometer detects any induced current. The secondary coil is not connected to any battery, it only has the coil and the galvanometer forming a closed loop. Part B2 asks why no EMF would be induced in the secondary circuit when the switch is closed and kept closed. When the switch is first closed, the current in the primary circuit rises from 0 to its steady value, and during this brief moment, the magnetic flux through the secondary coil is changing, and an EMF is briefly induced. However, once the switch has been closed and the current reaches a steady constant value, the magnetic field produced by the primary coil is also constant and no longer changing. According to Faraday's law, an EMF is only induced when there is a changing magnetic flux. Since the flux is now constant, no EMF is induced. The galvanometer returns to 0. Part B3 asks what should be done to induce an EMF in the secondary circuit. To induce a sustained EMF in the secondary circuit, the magnetic flux through the secondary coil must be continuously changing. This can be done by using an alternating current in the primary circuit. AC current continuously changes direction and magnitude, so the magnetic field it produces is always changing, inducing a continuous EMF in the secondary coil. Alternatively, repeatedly opening and closing the switch causes the current, and therefore the magnetic field, to repeatedly start and stop, inducing an EMF each time. Part C shows a transformer with 600 turns in the primary coil and 300 turns in the secondary coil, operated from 240 volts mains with an output of 120 volts. Part C asks for the power dissipated in the secondary circuit if the supply current is 2.0 amperes. For an ideal transformer, the input power equals the output power. Power in primary equals voltage times current equals 240 times 2.0 equals 480 watts. Therefore, the power dissipated in the secondary circuit is also 480 watts. Part C2 asks for one use of such a transformer. This transformer steps down from 240 volts to 120 volts. It is a step-down transformer. It could be used to power devices that operate on 120 volts from a 240 volt main supply, for example, powering electrical equipment designed for use in countries with 120 volt power systems, or in battery chargers, phone chargers, and electronic devices that require lower voltages. Now for question 11, rectification. This is one of the most technically detailed questions in the paper, and it explains the electronics inside almost every device you use. Let's walk through it carefully. Question 11, rectification and electronics. Question 11 tells us that all electronic equipment operating from AC mains must have a rectifier to convert the alternating current into the direct current needed for operation. Part A, Figure 11.1 shows the stages: AC mains A, then component B, then rectifier C, then component D, then component E, then DC output. We are asked to identify B, D, and E. Component B is a transformer, specifically a step-down transformer. It takes the high mains voltage and steps it down to the appropriate lower voltage needed by the electronic device. Component D is a smoothing capacitor. After the rectifier converts AC to a pulsating DC, the output still fluctuates. The capacitor charges up when the voltage is high and releases charge when the voltage dips, smoothing out the fluctuations into a steadier DC signal. Component E is a voltage regulator or stabilizer. It ensures the output voltage remains constant regardless of variations in the input or load. giving a stable, clean DC output. Part B asks us to name components S and R in the full-wave rectifier circuit. Looking at figure 11.2, the full-wave rectifier uses a bridge of 4 diodes. Components S and R are 2 of the 4 diodes in the bridge rectifier. So S is a diode and R is a diode. Part B2 asks us to explain how S, R, T, and U work together in normal operation. In a full-wave bridge rectifier, the 4 diodes are arranged so that current always flows through the load in the same direction, regardless of which half cycle the AC supply is on. During the positive half cycle of the AC input, current flows through diodes T and U. These 2 are forward biased and conduct. During the negative half cycle, the current direction reverses at the input, but now diodes S and R become forward biased and conduct instead. In both half cycles, the current through the output load flows in the same direction. This is how full-wave rectification works, converting both halves of the AC wave into DC. Part B3 asks for the purpose of the capacitor in the circuit. The capacitor is used for smoothing. After rectification, the output is a pulsating DC. It rises and falls with each half cycle. The capacitor charges up to the peak voltage during the peaks and then discharges gradually during the troughs, maintaining a more constant voltage. This smooths the output into a much steadier DC signal, which is essential for powering sensitive electronic devices. Part C asks, during the half cycle when Y is positive with respect to X, identify the conducting diodes. When Y is positive and X is negative, the current flows from Y into the bridge. Tracing the circuit, current enters through Y, flows through diode R upward, through the load, then through diode T, and exits at X. So diodes R and T are the conducting diodes during this half cycle. Part D asks us to draw a label diagram of a half-wave rectifier for DC output. A half-wave rectifier is the simplest rectifier. Draw an AC source connected in series with a single diode and a load resistor forming a closed loop. The diode only allows current through during one half of the AC cycle, the half when the diode is forward biased. During the other half cycle, the diode is reverse biased and blocks current. The result is that only positive half cycles appear across the load, giving a pulsating DC output. Label the AC source, the diode with its arrow pointing in the direction of conventional current flow, and the load resistor across which the DC output appears. And finally, our last question. Question 12 wraps up this paper beautifully with radioactivity, nuclear decay, half-life graphs, and the medical uses of radioisotopes. Let's finish strong. Question 12, Radioactivity and nuclear decay. Question 12, Part A, tells us that radioactive salt sodium chloride is used in medicine. The radioisotope sodium-24 with atomic number 11 decays to magnesium-24 with atomic number 12, releasing particle A. Part A asks us to name particle A. Looking at the nuclear equation, sodium-24 with atomic number 11 decays to magnesium-24 with atomic number 12. The mass number stays at 24, so the mass does not change. The atomic number increases by 1, from 11 to 12. An increase of 1 in atomic number with no change in mass number is characteristic of beta- decay, where a neutron in the nucleus converts into a proton, releasing a beta particle, which is a fast-moving electron. So particle A is a beta particle, also written as an electron with mass number 0 and atomic number -1. Part A2 asks for the number of charged particles in the nucleus of each atom of sodium-24. The charged particles in the nucleus are the protons. The atomic number of sodium is 11, which means there are 11 protons. Neutrons are uncharged. So the number of charged particles in the nucleus is 11 protons. Part A3 asks for one health effect of high consumption of sodium chloride containing radioactive sodium. High consumption of radioactive sodium would result in radioactive material being absorbed into the body. The beta radiation emitted by sodium-24 can damage living cells and DNA, potentially causing radiation sickness, damage to internal organs, increased risk of cancer, or in extreme cases, cell death. The radiation ionizes molecules in the body's tissues, disrupting normal biological processes. Part A asks for one radioisotope used in cancer treatment. Cobalt-60 is one of the most commonly used radioisotopes in cancer treatment. It emits gamma radiation, which is used in radiotherapy to target and destroy cancer cells. Another well-known example is iodine-131, used to treat thyroid cancer, because the thyroid gland naturally absorbs iodine. Part B asks us to plot a graph of activity against time using the data in Table 12.1. The data given is, at 0 minutes, 460 counts per second. At 10 minutes, 330. At 20 minutes, 230. At 30 minutes, 155. At 40 minutes, 105. At 50 minutes, 70. At 60 minutes, 50. Plot time in minutes on the horizontal axis from 0 to 60, and activity in counts per second on the vertical axis from 0 to 460. Plot each point carefully and draw a smooth curve through all the points. The curve should start high at the top left and gradually decrease, flattening toward the bottom right, a classic radioactive decay curve. Part B2 asks us to use the graph to determine the half-life of the sample. The half-life is the time for the activity to fall to half its initial value. The initial activity is 460 counts per second. Half of 460 is 230 counts per second. From the graph, draw a horizontal line from 230 on the vertical axis across to the curve, then drop a vertical line down to the time axis. Reading across at 230 counts per second, it reaches the curve at approximately 20 minutes. So the half-life of this radioactive sample is approximately 20 minutes. You can verify this by checking, from 460, half is 230 at 20 minutes. From 230, half is 115, which should occur at 40 minutes. From the table, at 40 minutes the activity is 105, close to 115, confirming our answer of approximately 20 minutes for the half-life. Outro. And that is it, everyone. We have completed the full 2024 Internal Pure Physics Paper 2, from micrometer screw gauges and energy on curved tracks, through pressure in dams, pulley systems, latent heat, sound waves, light and total internal reflection, series circuits, electromagnetic waves, magnetism and transformers, rectification, all the way to radioactive decay and half-life graphs. What a fantastic paper, and I hope this walkthrough has given you the clarity and confidence you need. Every topic that came up in this paper is something you can fully master. Physics becomes easy when you understand the concepts behind the formulas. If this video helped you today, please share it with everyone in your class, give it a big thumbs up, and most importantly, please subscribe to Mutal TV. Hit that notification bell so you are always the first to see our new videos. We have more past papers and physics tutorials coming your way. Until next time, study hard, stay motivated, and believe in yourself. I will see you in the next video. God bless you all. Goodbye.
That's sound. That's happiness. Forget everything you thought a cracker could be and say hello to Golden Crunch. Baked fresh daily.